Hello everyone. In this video, let's discuss about the application of eigenvalue problems. One of the main application is the stretching of an elastic membrane. The problem we are going to solve is an elastic membrane in the x1, x2 plane with boundary circle x1 square plus x2 square is equal to 1 gets deformed as given by the equation y is equal to ax, where A is a matrix with the elements 5, 4, 4, 11. Find the principal axis of deformation and the factors of extension or contraction. So first we should know how to find out the principal axis. So the principal axis of deformation represents an axis that doesn't get changed when it undergoes deformation. So the deformation happens in such a way that a point P, that is x1, x2, in the membrane will transform into point Q with coordinates y1 and y2. But along the principal axis, so like if we have a vector and then represent a position vector and mark the position of the point P and the position of point Q, so these two vectors, that is along the principal axis alone, these two vectors should be along the same direction or it should be antiparallel to each other. That is, you should get the position vector representing Q, that is y vector, when you multiply x vector by a constant. So this constant can be lambda, which is our eigenvalue. And this position vector is nothing but the eigenvector. So this is a simple eigenvalue problem. So we have to find out y, which is equal to lambda x, and we already know y is equal to ax. So ax is equal to lambda x. So this is a eigenvalue problem. Now the eigenvalue gives the factors of extension or contraction. That is mod lambda. If mod lambda is greater than 1, it represents extension, and if mod lambda is less than 1, it represents contraction. So that is less than 1 means it could be 0.1, 0.5, anything like that. So let's get into the problem. So first we have to find out the eigenvalue. So for that, let's write on the matrix A is equal to 5, 4, 4 and 11. So to find the eigenvalue, we have to equate the determinant of the matrix A minus lambda I to 0. So we know the matrix A and lambda is the eigenvalue and I is the identity matrix with the values 1, 0, 0, 1. So if we find out A minus lambda I, we will get 5 minus lambda, 4, 4, 11 minus lambda. So we have to find the determinant and then we have to equate that to 0. So to find the determinant, we will do the cross multiplication, that is 5 minus lambda into 11 minus lambda minus 4 into 4, 60. So that is equal to 0. And now we have to do the multiplication within the brackets and then we have to simplify it to get lambda squared minus 16 lambda plus 39 is equal to 0. So now we have a quadratic equation. We have to find the roots of this equation to determine the eigenvalue. And the root can be calculated using the formula minus b plus or minus square root of b squared minus 4ac divided by 2a. So here b is minus 16, a is 1 and c is 39. So minus b minus of minus 16 plus or minus square root of 16 square minus 4 into 1 into 39 divided by 2 times 1. So we know 16 square. So 16 plus or minus square root of 16 square is 256 minus 4 into 39 is 156 divided by 2. So that is equal to 16 plus or minus square root of 100. We know square root of 100 is 10. So 16 plus or minus 10 divided by 2. So to find out the first eigenvalue, we will use the combination 16 plus 10 divided by 2, which is 26 by 2, 13. And then To find the second eigenvalue, we will use the second combination, which is 16 minus 10 divided by 2, and that is actually equal to 3. So we have two eigenvalues, that is 13 and 3. So these eigenvalues represents the factors of extension, because if we take the mod value of the eigenvalue, this is actually greater than 1. So this is not less than 1, that is mod lambda 1, mod 30, and 3 is actually greater than 1. So these represents factors of extension. So the elastic membrane is stretched, not compressed. The principal axis. Now to find the principal axis, let's determine the eigenvectors corresponding to the eigenvalues 13 and 3. So the first eigenvalue is 13. So to find out the eigenvector, we have to use the equation again, lambda minus, we have to use the, to find the eigenvector, we have to use the equation A minus lambda I into x is equal to 0. So that is the equation that they are supposed to use. And we know A is 5, 4, 4, 11. And then when we do A minus lambda I, we will get 5 minus lambda, 4, 4, 11 minus lambda. So instead of lambda, we have to substitute 13. So that is 5 minus 13, 4, 4, 11 minus 13. Multiplied by x1, x2. Now this is equated to 0. So we know 5 minus 13 is minus 8. And 11 minus 13 is minus 2. So now when we do the matrix multiplication, we will get minus 8x1 plus 4x2 is equal to 0. And similarly, second row multiplied by the column vector, we will get 4x1 minus 2x2 is equal to 0. Both the equation will yield the same result when we do the simplification. That is 4x1 will be equal to 2x2. So that is x2 is equal to 2x1. Now we have to substitute value for x1 to determine x2. So let's put x1 is equal to 1 and we will get x2 is equal to 2. So this is the first eigenvector. Now let's move on to second eigenvalue, that is lambda 2 is equal to 3. We will do the same procedure and then we will find the second eigenvector. So here 5 minus 3 is 2. So 2, 4, 4, 11 minus 3 is 8. So 8 multiplied by x1, x2 is equal to 0. So when we do the matrix multiplication, we will get 2x1 plus 4x2 is equal to 0. And 4x1 plus 8x2 is equal to 0. Again, both the equation will yield the same result. That is 4x1 is equal to 8x2 or 2x1 is equal to, both the equation will yield the same result. That is 4x1 is equal to minus 8x2 or 2x1 is equal to minus 4x2, which will give us x1 is equal to minus 2x2. So now we have to substitute value for x2 to find out x1. So let's put x2 is equal to minus 1. We will get x1 as 2. So these are the two eigenvectors y1 and y2. So in order to visualize the deformation, first we have to find out the angle between the eigenvector and the positive x1 axis. So let's take the first vector y1 is equal to 1, 2. So if we plot it in the x1, x2 plane, so this point will be in the first quadrant with some theta. We have to find out theta. So let's draw it as a triangle. We will get right angle triangle with adjacent value 1 and opposite value 2. So if you want to find out tan theta, we will get tan theta is equal to 2 by 1. That is x2 by x1. So theta is equal to tan inverse of 2. That is nothing but 63 degrees. And similarly, we have to do it for y2. So y2 is a column vector with elements 2 and minus 1. And when we plot it in the x1, x2 plane, we know x1 is 2 and x2 is minus 1. So this will be in the fourth quadrant. and the angle is theta. So here again using the same formula, theta is equal to tan inverse of x2 by x1, we will get tan inverse of minus 1 by 2. So now the theta is minus 27 degrees. So we have to plot it in a graph to visualize the deformation. So initially the membrane is a circular membrane, which is given by the equation x1 square plus x2 square is equal to 1. That is, this is a circle with radius 1. Now when it undergoes deformation, the deformation will be along the principal axis. So first we have to plot the principal axis. So we know the first eigenvector is along the first quadrant. So this is the point 1, 2, and then we can represent this point using a position vector, and then when we extend this position vector, we will get the principal axis. And then when we plot the second eigenvector, we will get it in the fourth quadrant, that is 2, minus 1, and then we can again use the same position vector, and then we can extend it to get the principal axis. Now the angle between the positive x1 axis and the eigenvectors can be plotted, which is 63 degrees and minus 27 degrees. So along the first eigenvector, the stretching is maximum, and along the second eigenvector, the stretching is minimum. So in order to find out the factors of extension, how much it got stretched, we have to look at the eigenvalue, because the eigenvalue corresponding to the eigenvector 1 and 2. There is a column vector 1, column vector with elements 1 and 2 is 13. So along this principal direction, the membrane got stretched about 13 times. And then along the second eigenvector, because that second eigenvector corresponds to the eigenvalue 3. So along this direction, the membrane got stretched for about 3 times only. So in this problem, we have determined the eigenvalue and the eigenvector corresponding to the deformation line. So using these values, we have visualized the deformation. So the circular membrane got stretched into an elliptical membrane with principal axis along the direction given